Okay, so welcome to the 40th video in the Discrete Structure series and a continuation of the chapter Counting and Discrete Probability. In the last couple of videos, we have finished looking at the basic principles of counting and the pigeonhole principle. So from this video, we'll be starting a new topic, and that is permutations and combinations. So our goal in this video will be to introduce these concepts, and then we'll explore a few rules and formulas to be careful about in this topic, and then we'll have a section in our video where we'll be solving numerical problems. So let's get started with our first agenda, and that will be an introduction to permutation and combinations. So I think it would make a lot of sense to discuss both of these topics in parallel, and then we'll go through problems at the end. Alright, so both permutations and combinations are ways of arrangement. And what does it actually mean? So let us see with an example. I'll consider a set S with three elements A, B, and C. And I want to ask the question, in how many ways can we select two items from this set? And because this is a relatively small set, we can try to actually list all of the two item selections from the set. So I know that when I select two items, I'm going to have either A, B. And this happens when I pick A and then B. But I could have also started by choosing B. There's more that I'll talk about this shortly, but for now, let's just list it. So BA is another permutation. And I get these two permutations when I'm considering A and B, right? Two elements. If I were to consider B and C, I get two more permutations. It's going to be either BC or CB. And finally, if I were to consider the elements C and A, I would get the permutation CA and AC. And so this list covers the 6 different permutations, taking 2 at a time from this set. And before we lay a similar example for combinations, let's understand one more point. We want to be able to observe that in this case, the order of selecting the elements does matter. And by order, we mean the order of picking the items from this set. So when I formed this permutation AB, I started by picking A and then picked B. So that means A was chosen first and B was chosen second. And this specifies a specific order of choice. And because order does matter, choosing B first and then A second would give a different permutation. Therefore, when we are listing permutations, I want to list the elements in a particular order. And if I were to now repeat the same example for combinations and the same question. And this time we are simply mentioning that we do not want to care for any specific order. Therefore, in terms of combinations, these two choices where A was chosen first and B was chosen second, and this choice where B was chosen first and A was chosen second would form the same combination. Because it is just a combination of A and B. And similarly, these two permutations of B and C will be a single combination of B, C. Similarly, I'll have a single combination of C, A. And from this, we can observe that there are only 3 possible combinations when I choose 2 items from a set of 3. And we're really close to formalize this, but let's make one more observation. So instead of selecting 2, if I were to select 3, selecting all at a time, how many different permutations would I get? And before I come to permutations, let's look at combinations. How many different combinations do I get if I select all at a time? See, if I select A, B, and C, all of them, this is really the only combination that is possible. Because I'm not allowed to interchange the positions of B, A, and C and call it a different combination. Therefore, if you are taking a combination of n variables taken all at a time, you have to take all of them. There is no other choice, and there will be only one combination. But if you look into permutations, it is the permutations of the same items A, B, and C. But since order does matter, I get multiple permutations because I could choose A first or B first or C first. And even after the first choice, the second and third choice will still have options. So in order to list the 6 different permutations, I'll fix A first in 2 of them, and then I'll say BC and CA. And I'll add B and C in both orders. So I'll say BC and then CB. Next, I'll fix A in the middle. For 2 cases, I'll say CB and BC. Similarly, if I fix A at the end and mention CB and BC, I can see this generates 6 different permutations if I select all 3 at a time. Alright, next we'll have a quick analytical look at these concepts and also look at the formulas. So let me do the same thing again. I'll have 2 columns for permutations and combinations. So let's start by generalizing the previous example. So I considered 3 elements in my set before, but this time I want to generalize and call that this as any number of elements n. And we looked into the cases where we selected 2 at a time and 3 at a time. But we want to be general again and we want to select R at a time. And since this is a permutation, order matters. So this job of selecting n elements r at a time while making sure that the order matters is called a permutation. This is denoted by the expression p n comma r, and this just says select r from n, and p suggests that the order does matter. And this is also sometimes denoted as npr. But through this course, we'll be preferring this notation. Alright, so let's try to evaluate what this will be equal to. So I want to be able to select r objects from this set. So it is just like the product rule and the basic principle of counting. If I choose r different spots where the selected elements will go to, I know that this very first position has n different choices because any of these n elements could be chosen to fill the first spot. So this has n different choices, and once the first spot is filled, there are only n minus 1 possibilities for the second spot because one of these elements would already be gone. So we'll just put n minus 1 here, and then if we continue on this chain, n minus 2 possibilities here, n minus 3 possibilities here, and where does it go to? So let's try to find out what the rth term would be, and we should be able to observe this. For the first term, I'm taking n minus 0, okay, because there's nothing here, n minus 0. For the second term, I'm taking n minus 1. For the third term, I'm taking n minus 2. So what I need to subtract from n should be 1 less than the term that I have, okay. So when I reach my rth spot, 1 less than r is r minus 1. So what we'll actually have here is just going to be n minus this quantity. And if I expand this inside the bracket, I get the term as n minus r plus 1. So let's continue this. I'll just clear up a little bit of space. So next we'll try to do a little bit of arrangement here. We'll say n minus 1, n minus 2. I'm including all the terms. It goes all the way to n minus r plus 1. And if you really inspect this, it is just a product that starts with n, and each term is 1 minus the previous term, okay? From n minus 1, subtract 1 more n minus 2, subtract 1 more n minus 3, and eventually we hit this value. So let me keep multiplying with other terms, and then we'll divide to cancel out. After this, what would you normally expect? 1 less than this value would just remove this 1. So the next term would be n minus r. The next term will be 1 even less than this, n minus r minus 1. And where do you think this is going? It is going all the way to 3, 2, and 1. Because each time we're decreasing from n, and then we're taking a product all the way up to 1. But I'm not allowed to do this. I'll need to divide it by the same quantity in order to maintain the balance. So I'll write the same thing here, n minus r minus 1, all the way up to 3, 2, and 1. So what I'm really doing is just saying this is equal to this value. And then I multiplied and divided by the same quantity. And doing this has an advantage. It condenses the formula. Now I can see the full term in the numerator is a continuous product from 1, 2, 3 all the way up to n. We know that is equal to n factorial. And if you look at the denominator part, it is also a continuous product, but only up to n minus r. So this denominator is simply n minus r factorial. And there you go. This is the formula that we tend to use in order to compute the permutations of n objects r at a time. And in order to derive a formula for combination, we need one more result from permutations. And that is the case when all objects in the permutations are taken. So what happens when r is equal to n in permutation? So it's just like having 5 elements and looking at permutations of all 5 of them. And this formula simply tells us this is going to be equal to n factorial by n minus n factorial. So this is n factorial by 0 factorial is just equal to n factorial, because 0 factorial is just equal to 1. Now, in order to calculate the combination Cn comma r, we'll start with all of the permutations. So we have n factorial by n minus r factorial. And this formula is not complete, but I want you to observe that when I'm taking r items, in this formula, I do care about the order because it is a formula from permutation. So all of the different arrangement within r are also being counted here. From our formal example, we had a set with 3 elements a, b, and c. And let's say we are taking 2 at a time, r is equal to 2. Then if I want to choose any combination of 2, a comma b, I only want this to be counted once, a and b. But what is this formula doing? It is counting this twice. It is counting a, b, and also b, a, because this is a permutation and I don't want to count these duplicates. So how many duplicates am I actually counting? What if this was a larger set with a, b, c, d and r was equal to 3? Then for any combination like a, b, and c, we just saw in our earlier example that this has 6 different permutations. And this time I want to count all of these 6 as just one combination of a, b, and c. But I know this formula is counting all of the 6. So it turns out that for any r I choose, I want to eliminate all the permutations between R. Okay, listen to that again. For any R like 3, I want to eliminate all the permutations within 3. And I can look into the formula. The permutation of an object taken n at a time is just n factorial. But this time I want to do the same thing with the R choices that I made inside of the combination. So this formula simply tells if I choose R objects all at a time, I get R factorial different permutations. Therefore, in order to compute the combination, we'll divide this number of permutations by the term R factorial. If I have 6 different possibilities and I divide it by 6, I just get a 1. So in order to combine all of these 6 possibilities into one possibility, I just divide with the number of possibilities. And therefore, the formula for combination Cn, R can be written as n factorial by n minus R factorial times R factorial. So just basic algebra, this is R factorial by 1. When I transpose this to the numerator, R factorial turns up in the denominator. So this is our final formula for combination of n objects taken R at a time. And this will be for the permutations of n objects taken R at a time. And now we're ready for problems, but there's one little thing in combination to talk about. We want to establish this fact. The combinations of n objects taken R at a time is the same as the combination of n objects taken n minus R at a time. So the easiest way to prove it is just to use this formula. I'll not be doing it here, but I'll show you a logical reasoning behind why this works. So let's say I'm choosing combinations. I'll take the same example with just 3 items at this time. And then let us consider R is equals to 2. Then what this formula is suggesting me that the combination of 3 objects taken 2 at a time is the same as the combination of 3 objects taken 1 at a time. Because my n is equal to 3, R is equals to 2. That means this n will still be 3 and n minus R will be 3 minus 2. That will be equal to 1. And the reason why this is true is because every time I list a combination in 3, 2, I can list an equivalent combination in 3, 1. And the main reason, I'll mention it here, the number of ways to choose something is equal to the number of ways to not choose those things. And let's come back to this example to make it even more clear. So when I'm selecting 2 at a time, and this is just a combination, right? So selecting AB is the same as selecting BA. So when I list a combination of A, B, I did a job of choosing A and B. But what does it really mean to choose? When I chose A and B, I created a gap. I separated AB from C. Therefore, a choice of AB is the same as the choice of the single term C. So if I can get a combination by choosing A and B, I can get an equivalent combination by not choosing A and B. And that will lead me to choose C. Similarly, in my combination, if I think of choosing B and C, my act of choosing B and C is equivalent to the act of choosing A. So if choosing B and C gives a combination, not choosing both B and C gives another equivalent combination, and that gives me A. And if I were to take a combination between A and C, not choosing A and C gives me B. That means the item in the combination 3, 2 have a 1-to-1 relationship with all the items in the combination 3, 1. And that happens because anytime I choose R, I'm also making an equivalent choice in the items n minus R. So this is my third useful result. So apart from all of the concepts, the things that you need to remember is going to be this formula for permutation, this formula for combinations, and this special rule for combinations. Now there are more topics in permutation and combinations like circular permutations, permutations for indistinguishable objects, and a few other topics. But we'll just flow with the course and syllabus. And there is this topic of binomial coefficient and Pascal's triangle that we'll do next. And then we'll eventually get to those topics. But for now, let's get started with the problem section of our video. So I'll put my first question here. In how many ways can we select a group of 3 students from a total of 5 students? And then we are given 2 cases. The first one says for a school picture, and the second one says for a student committee. And here's something to understand. It's really important for you to recognize by looking into the question whether they are expecting a permutation or a combination. And we should always be aware of the core philosophy that for a permutation, the order does matter. But for a combination, the order does not matter. So in any question, whenever we are taking R items from a set of n items, we are going to look into the purpose of what the goal is. And that will hopefully tell us if the order matters or not. Now this example is kind of vague, but this should also give you some sense. So we are selecting students for a school picture in this case. Whenever you're taking a picture, the order does seem to matter. And I am just being general. A picture with A on the left followed by BC is considered to be a different picture that has B at the start followed by A and C, for example. So in this case, we'll decide that the order does matter and therefore we'll be using a permutation. In this case, I'm selecting the 3 students for a student committee. A committee with A, B, and C is the same as a committee with B, A, and C. It's just the people A, B, and C in the committee. So when I'm considering a student committee, it doesn't really matter in which order I pick the students. As long as I've chosen the same set of students, I can consider them to be a same combination. So this question is not tough at all. My intent is just to give you an idea of how you know whether to apply a permutation or a combination. In this case, it is just equal to P5, 3, choosing 3 from a set of 5, and this gives you 5 factorial divided by 5 minus 3 factorial. And this will just be equal to 60. And on the other end, I'm looking at C5, 3, the combination this time of taking 3 students, and I can simply apply my formula. This will be equal to 5 factorial by 5 minus 3 factorial times 3 factorial. Now I know 5 factorial by 5 minus 3 factorial is just equal to 60. 60 divided by 3 factorial is just equal to 6. And now this will just give me 10. So pretty basic solution. We'll move on to the next question, but there's something that I remembered. I'll mention it quickly. So let's say I have 5 numbers, 1, 2, 3, 4, and 5. And I want to do the same thing. I want to choose 3 numbers from this list. Should I apply a permutation or a combination? Should it be permutation or a combination? And if you guessed permutation, I'm sorry, that was incorrect. And if you selected combination, I'm sorry, that was incorrect too. Because going back to the philosophy, I do not know what this choice is for. What am I really choosing these numbers for? Does order matter? If the question says I'm forming different numbers by choosing these digits, I know that the number 231 is different than 312. And this is different than 123. So different choices of 1, 2, and 3 will result into different numbers. So if my goal is to form these numbers, I'll be choosing a permutation because I know that the order does matter. But let's say I'm making the same choice in order to reach a particular sum. Okay, I want to choose 3 items so that their sum is 6. And to do that, I want to list all the possibilities of 3 different items. Now in this case, if I add 2 plus 3 plus 1, I just get a 6. If I add 3 plus 1 plus 2, it's just 6. So any permutation of 1, 2, and 3 will just add up to 6. So if my goal is to make these selections and then look at the sum later, I really do not care about the order. And in the same problem and the same choice, I'll be applying a combination. So this is a really important concept. So it depends on the problem and the goal in order to decide whether to apply a permutation or a combination. Alright, moving into a few other questions. In how many ways can we assign 3 prizes? And it says it's the first, second, and third prize to 100 people. So it's pretty obvious that I need to select 3 people from a set of 100 to be able to assign these prizes. But the big question is, does order matter? So I have my 3 spots for first, second, and third prize. Now if A gets the first prize, B gets the second prize, and C gets the third prize, is it the same as this one? With A getting the second prize, B getting the first prize, and C getting the third prize? No, these two are different. Therefore, when I'm selecting my 3 people, the order in which I select does matter because I'm providing the first prize to the first person that got selected. So being selected first is different than being selected second. So we can conclude that in this problem, the order does matter and we'll be using a permutation. The answer itself is pretty simple. All I want is a permutation of 100 students taken 3 at a time. And you can just do the math. This will just be equal to 970,200. Now what happens? In the same question, I remove the tires. Okay, there is no first, second, and third. There are just 3 prizes. And to make it even more clear, I'll just say 3 consolation prizes. And we'll also assume that all prizes are the same. Okay, so everybody gets the same prize. This is P, and the same prize must be given to 3 people. Now in this case, if I select A first, B and C, all of them received the prize P. If I put A here, B here, and C here, it is no different because all of them still received the same prize P. So the point to understand that the exact same question and the exact same requirement could be framed for you to use a combination. So if all prizes were the same, I'd just be looking at C 100, 3. So I'm doing this to hopefully make you guys realize the importance of understanding the question. It is really important for you to be able to see the question and to decide whether to apply a permutation or a combination. Alright, moving into one more problem. Suppose that a salesman has to visit 8 different cities. The trip must be begun in a specific city, but the remaining 7 cities can be visited in any order. How many ways can he complete his travel? So this is also a pretty simple question. We have a set of 8 different cities, and according to the question, the trip must begin in one of these 8 cities. So the first city that the salesperson travels to is already fixed. And without losing any generality, let's assume that C1 is the first city that they must travel to. And once they are on C1, they can choose to go to any of the other cities. Now we could just use the principle of counting, but all we're looking for is the number of ways in which we can find permutations of these 7 objects. So since one city is already fixed, the number of ways of permuting 7 different cities is the same number of ways that he can complete his travel. So we can frame the solution in this way. There is only one choice for the first city because it is fixed. The permutation of remaining 7 cities is the number of ways he can complete his travel. Therefore, the total number of ways, and this will just be equal to 7 factorial in this case, and this is just equal to 5040. So there are 5040 different ways for the salesman to complete this tour. And you should be absolutely clear that the answer is really 5040 times 1, and this 1 comes from the one choice that we have for the first city. And like we always do, let's try to do a small modification on this question and see what implication that has. So I'll just make a small change here. The trip must be begun in 2 specific cities, okay? Not just 1, 2 specific cities, and then I'll say in any order. And the remaining 7 cities or the remaining 6 cities can be visited in any order, okay? So I just made a very minor change. So instead of starting with just one city, there are 2 specific cities that they must attend first and second, but they can attend it in any order. So with the same train of thought, if C1 and C2 are the 2 cities that they must travel to first, we are saying that they can travel C1 and C2 in any order, and once they finish doing that, they can travel C3 to C8 in any order again. And how would this affect your solution? Now we are not just looking at the first city, but the first phase of the tour. And then there's the second phase of the tour. So during the first phase, he has to visit the cities C1 and C2. And that will just give me 2 factorial and equal to 2 possibilities. And this should be clear. The 2 comes from the fact that I can start with C1 and then visit C2. And there's another way. I can start with C2 and then visit C1. So there are 2 ways to do the first phase. Now for the second phase, the argument will be exactly the same, but instead of 7 factorial, we'll be getting 6 factorial. And what you definitely don't want to do is to say that 6 factorial is your answer, because that is not. Your actual answer would be 6 factorial times 2 factorial. Okay, so for each way of completing the first phase, all of the ways of completing the second phase apply. So I hope this makes sense. Since there was only one choice, I didn't have to do anything. But what I'm really doing is taking 1 factorial. So please be aware, you want to be able to solve problems of all of these classes. Moving on to the next one. And this one asks, how many permutations of A, B, C, D, E, F, G, H contain the string ABC? So I know for these 8 given letters, there are 8 factorial different permutations. But not all of those permutations will contain ABC. For example, one of the permutations could be A, D, E, F, G, H followed by B, C. This is a valid permutation, but it does not contain ABC anywhere. Okay, so we want to count the permutations that actually contains ABC together. So how do we actually solve this problem? So the concept of grouping comes into play. So I have 8 different spots and I have to put A to H in here. But what I want is for the pattern ABC to always be together. So what I want to do is to lock the species. I want to lock this between A and B. This should not be changed. And I want to lock this between B and C. This should not be changed. And other things can be changed. And what does it technically means to put a lock here? It means that these 3 things will always be together. And these 3 spots will always be related to A, B and C. So wherever A comes, the next spot will be for B and the next spot will be for C. So we can consider the string ABC as a single letter. And we can assume that they are sitting in a single position. And by doing this, we can reframe the question as having 6 spots and 6 different letters, considering A, B, C as the single letter. So 1, 2, 3, 4, 5 and 6. So the number of ways 6 things can be arranged in these 6 positions is the solution to this answer. Because you should imagine A, B, C are always together. What if this is A, B, C? Ultimately, this is just 3 spots, right? With 1 on A, 1 on B, and 1 on C. So it is actually equivalent to 1, 2, 3, 4, 5, 6, 7 and 8, like in my original question. But since I'm grouping all of these 3 into a single position, all of the positions will also be grouped together. So with that idea, let's get into the solution. Since we want to ensure that the string ABC always occurs, we can treat the string as a single letter. So this reduces the problem to one with 6 letters and 6 positions. Therefore, total number of permutations, and this will just be equal to 6 factorial, and this will just be equal to 720. So this is also a really important type of a problem where you need to group some items and positions in order to calculate the permutation. Alright, moving into the couple last problems for the day. How many poker hands can be dealt from 52 cards? Also, if a poker hand hypothetically had 47 cards, how many hands would there be? So this is a problem on combination and a really simple one. So I have my total of 52 cards and I want to select 5 cards at a time in order to form a poker hand. Now whenever you are playing a card game, does the order in which you receive the cards matter? No, because whatever order you receive your card in, your hand is going to be the same. So in the game of flush, that is really common in Nepal and is also really similar to poker, and a set of 3 aces is considered the most powerful hand. Now if you get this ace first and this second and this third, does your hand become any more powerful or less powerful if you receive the cards in a different order? No, because no matter what order these cards are dealt in, the hand is always the same. So what you're looking for here is not the permutations but the number of combinations. So in this case, we're talking about poker, and from 52 we're choosing 5. So my answer is just 52, 5, and I'm taking a combination. This will come up to be 2598960. And now moving on to the second part of the question. If a poker hand hypothetically had 47 cards, how many hands would there be? And we discussed in the earlier segment of the video, anytime I select 5 cards, I am also selecting the remaining 47 cards. Therefore, the combination of 52 items taken 5 at a time is the same as the combination of 52 items taken 47 at a time. And this is because 47 is equal to 52 minus 5. We know that CNR is equal to CN n minus R. And therefore, this number would also be equal to 2598960. Alright, another question. How many bit strings of length n contain exactly R ones? So the question is asking that if you are given any length string n, so let's consider that n is equal to 4. And I know that if I list all of the bit strings of 4, it starts with 4 zeros and ends on 4 ones with everything in between. And my job is to count the number of these items which contain exactly R ones. Okay, so I'm looking for exactly 2 ones, for example. So let us try to evaluate this. I have 4 positions and there are 2 ones that I must place here. And once I fix the position of ones, the position of zeros are automatically fixed. So that doesn't need anything to be done. Now to understand whether we want to apply a permutation or combination, let's name these positions P1, P2, P3 and P4. So in this case, my job is to put 2 ones in 2 of these 4 places. Now, let's say I decide to put ones on P1 and P3. Okay, so I'll put 1 on P1 and also a 1 on P3. So does the order of doing that matter? So if I put 1 on P1 first and then 1 on P3 second, that will give me 1010, right? 1010 will be my number. But if I put 1 on P3 first and 1 on P1 second, does that make a difference? It still doesn't make a difference because I still get 1010. So when I want to put R ones in these n spots, the order in which I put the ones does not matter. Because whatever order I put them in, once I've finished putting all of the ones, it will give the same final number. And this is precisely the fact why we want to take the combination. So we'll formalize this answer quickly. The required number of bit strings is obtained by placing a 1 in exactly R out of n positions. You should mention this. The order of placing a 1 does not matter, and once all of the ones has been placed, the remaining positions will be taken by a 0. And therefore, the final number obtained by this placement does not depend on the order in which the ones are placed. So once you mention that, you are now free to mention that the required number of OH is the same as the combination of n things taken R at a time. Alright, one last question for the day. Suppose there are 9 members in the mathematics department and 11 in the computer science department. Considering 5 people from the mathematics department and 4 from the computer science department, in how many ways can a committee be formed? So this is another typical form of question that you want to be prepared for. So we'll first start looking by considering 5 people from the math department. So I want to select 5 people from a group of 9 members that are in the math department. And is this a permutation or a combination? We know that this is a combination because if I select a committee of A, B, C, D and E from the math department, a committee of C, B, A, D and E can also be considered as the same committee. So the order of selection does not matter here. Therefore, the number of ways to choose 5 people from the math department is given by the combination of choosing 5 people from a group of 9. And with calculation, I can tell this is equal to 126. Next, we want to look at the possibilities of 4 people from the computer science department. And similar to the first case, this time we are looking at a combination of 4 people chosen from a group of 11 people. So this is just going to be a combination of 11, 4. And this value is equal to 330. And what is our final step? The final step is to apply the product rule because you can see that there are 126 ways to choose 5 people from the math department. And if I select any one of these choices, I can repeat all of the 330 choices in the computer department. So this particular combination from the math department, when combined with all of the 330 combinations from the computer science department, give me 330 different possibilities for my final answer. And this will also be true for the second combination that I take, and the third one, and the fourth one, all the way up to 126th combination. So we have already done this discussion in the past, but from the product rule, we know that for each of the combinations in the math department, all of the combinations in the computer science department will repeat. Therefore, the total number of committees will just be the product of these two values, will be equal to 126 times 330. And the result of this is just going to be 41,580. So this is also a really common type of problem where you need to take combinations in distinct groups and then apply the product rule to calculate the total number of combinations. And with this problem, we have completed the discussion for today's video. So we'll start next video with an interesting topic of binomial theorem and Pascal's triangles. So that is all for today. I'll see you guys in the next one. Have a good day and bye.